My name's Nate Hoover,
I'm Ryan Deptula.
and this is a presentation on the calculus of acoustics. So just to start off with some basic stuff, we have wavelength and frequency. Sound is caused by a vibration, any type of vibration, from a source and a receptor. So as I'm talking, my vocal cords are vibrating, your eardrums are vibrating at the same time, as long as you're close enough to hear me. The number of vibrations per second is called hertz. It's called the frequency. The range of a human's hearing is between 20 hertz and 20 kilohertz. The wavelength is related to the frequency by the speed of sound divided by the frequency. So the basic physics of sound waves, they can be described as a transverse wave, meaning the displacement of the air molecules is perpendicular to the direction in which it travels. So the sound that I'm projecting, the displacement of the air molecules is in this direction. And it can be related by the amplitude times the sine function of the wave number of x minus the angular momentum with respect to the time. And it is related to the pressure and density through which the medium it travels by the equation negative PM, which is the pressure, times the cosine of in kx, and omega t is in the same as it was in the displacement function. Differentiating each of those, you see you have basic calculus, such as the negative, and you get cosine out of that, and the sine from the cosine. And since they are related to each other, you can get the speed of sound by some manipulation of the equations to ultimately equal v, which is the speed of sound, which equals the square root of gamma times the P is the pressure, and then rho is the density through which it travels. And gamma in normal at 1 atmosphere is 1.4. So the wave equation for a regular wave is described as the second order partial derivative of the displacement of the air molecules with respect to the time, which equals the inverse of the speed of sound times the second order gradient with respect to the position in which it travels. Note that in some point in time, you have where both of those are equal, which implies that at some position and at some time, as the sound travels, it's going to equal to the sound that's around it. And then you solve the wave equation for 3D, which you see here, where F and G are from the point source, from where the sound is coming from, and the R and C is this radius and circumference.
C is the velocity of the wave itself, and R is the radius of the sphere itself. So as the wave goes through space, as you see here, there's different varying levels of spheres, and each one has its own radius. So that relates to the displacement of the sound itself. Now, some applications of calculus using sound is one of the first you get to understand. There's a Fourier series, and the Fourier series, a mathematician in the 19th century named Joseph Fourier described the ability of certain sinusoid graphs to take the shape of any sinusoid graph by a addition as a sum of all these graphs. And you can produce, if you see this little animation here, you have a certain function or curve here, and that curve is actually created by the addition of multiple sine curves using this equation right here, where the a of sub n of cosine nx plus b of n of sine nx equates to that function you're trying to find. And you can use this. Actually, the creator of the Fourier series themselves was a French mathematician born in 1768, and he did most of his work in the 19th century. He is really known for his work of heat transform and vibrations, which resulted in the Fourier series themselves, and the Fourier transform, which is using the previous noted sum to create the new function. You can actually do a reverse Fourier transform where you take a curve that was shown before, that curve, you can find the addition of all the sinusoids using a different Fourier transform. And he published his Fourier series in his work, The Analytic Theory of Heat, which was published in 1822. And he claimed that, like I said earlier, that any function can be expanded in a series of sines and multiples of the variable. And one application of this is in digital processing. In digital processing, you need to determine a rate at which you collect data samples in order to get the correct sound recording. And the Nyquist theorem was used. The Nyquist theorem takes the Fourier series in the sense that sound waves are usually sort of like a sinusoid-esque shape, and some of them have crazy shapes, so you can find the equation needed using the Fourier series to find the exact equation for that sine wave. And the Nyquist theorem states that any signal, you can perfectly reconstruct that signal by taking the highest frequency and multiplying it by 2, and that's the number of samples you need per second. And as an example for this, it shows if you have a sample signal of a frequency of 1 hertz, you have this graph right here. And using the Nyquist theorem, you need to have 2 samples per second, and that creates a point right here, point right here, point right here, etc., etc. Now, however, if you take a sample signal of 1.5 samples per second, you get a point here, point there, point there, point there, and the perceived sound wave of the previous samples is this, which is incorrect from the original one. So you need to have twice the highest frequency of the original sample. And another application of calculus in acoustics is using, for the Norwegian folk flute, which I'm not even going to try and pronounce that. It's actually a flute made of a hollow willow tree, and you take one end is closed, and there's a hole at one end where the player blows in, and the other end is open. And there's an equation here, u of xt equals sine of bx times a sine of the quantity abt plus c, where a, c, and b are all constants to be determined later. And the way the player differentiates between tones is using harmonics, and that they vary the pressure that they push into the flute itself. And solving for when u of x of t equals 0, you attain these values where n is a certain constant depending on the amount of pressure you put forth into the flute, and they can be directly related into the frequency of the output of the flute itself, which will directly correlates to the pitch of the flute itself. So the higher the frequency, the higher the pitch, the lower the frequency, the lower the pitch produced based on the pressure. And that was really our presentation on calculus of acoustics. Thank you so much for listening, and